everyone. My name is Nicolas Lepage-Saucier. I'm a labor economist and applied econometrician. So the motivation for this project was my last revision. We had 6 months to do it, and the computation alone took exactly 6 months. So I decided to switch to a better language, and I started thinking about numerical methods. So I will briefly explain what speed mapping is, and because of time, just what the words in the title mean, and then show how the package works, and then show some benchmarks. So speed mapping accelerates fixed point mappings, which are ubiquitous in many domains of science. I have emphasized some that have applications in the paper. So some background, many of you will be familiar with Newton's method for finding the roots of a function. So Aitken's delta squared process is the same idea for mappings, since at the fixed point, f of x minus x should be 0. So we know this first difference, delta x, and we approximate its derivative by evaluating f twice and then using the secant method. So here the numerator is the change in delta x following a mapping, which we write delta squared x. So Le Maréchal's method is a vector version of Aitken's delta squared process. It has the flavor of gradient descent, since the step size is just a scalar, it's just a ratio of two inner products, so it's very easy to compute. Next step in the story, the Cauchy-Barzilay-Borwein method. So to understand it, realize that Le Maréchal's extrapolation is itself a mapping with the same fixed point as f. So with little extra calculation and using the same step size, we can cycle a second time through the data and get for free this squared extrapolation. Now the new proposal is a generalization of this idea to higher orders. So I show in the paper that alternating between order 3 and 2 extrapolations speeds up convergence considerably, and using the absolute value of the step size improves stability a lot. So for further detail, I invite you to look at the paper. Now let's have a quick demo of the package. I have created a Jupyter notebook with 2 examples. The first one will be finding the dominant eigenvalue of a sparse matrix using the power method. So it's used by companies like Google to recommend pages or Twitter to recommend users. Here are the packages we need. So the power method can be very fast, but it can also take many iterations if the matrix has a wide spectrum, meaning if the eigenvalues vary a lot in magnitude. So let's give it a hard time and do just that. So we generate this sparse 100 by 100 matrix where we're going to add to the diagonal elements these random numbers between 0 and 100. So the power method is already implemented in Julia in iterative-solvers.jl. Here I'm timing it with p time. So as you can see, it took over 3,000 iterations and 5 milliseconds, so not too impressive. One way to improve the results would be to use the Krylov-Schur algorithm implemented in Krylov-Kit. So indeed, it finds the solutions much faster in under 1 millisecond. But there may be a better way. So instead, we can keep the power iteration as it is and just accelerate it with speed mapping. So I've written it here. It takes a non-zero vector x in and multiplies it with the matrix A in place. Then we have to scale down the vector to keep the numbers reasonable. So I've made the syntax of speed mapping as simple as possible. It takes a single regular argument, the starting point, here just a vector of ones, and a single keyword argument, and bang, our power iteration. So we had to beat 3,000 iterations. Success only needed 139 iterations, and it took less than half the time of the Krylov-Schur algorithm. We can convince ourselves that we got the same answers. Okay, let's jump to the second example, accelerating gradient descent. So I've chosen the classic Rosenbrock function, which is a 2-variable function that looks like a curved canyon with minimum at 1, 1. So it can be challenging to optimize if we don't have a good algorithm. But let's be ambitious. We have a good algorithm. So instead of 1, we're going to add together 500 Rosenbrocks for a total of 1,000 variables. And for extra fun, let's have a not so clever starting point, a range between -5 and +5. So I made the syntax of speed mapping as close as possible to that of Optim.jl. Here it takes 2 keyword arguments, and f and gbang. So in converge in the 452 maps, or in that case, that's 452 gradient evaluations. It also used even evaluations of the objectives to give the gradient descent a good initial step or a good initial learning rate. But if you're in a hurry and you don't want to provide f, no problem. It's going to take the gradient to initialize the descent step size. You can also omit g, but then of course you have to give f. So it's now going to use autodiff to compute g and take a bit longer. Finally, something I've implemented 3 weeks ago, box constraints. Here, let's impose that the first coordinate of the Rosenbrox be at most 0.5 and no restriction on the second coordinate. So in that case, it should all converge to 0.5 for x and 0.25 for y. All right, so is that any fast? So I'm sure at this point you want to see benchmarks. So I'm going to compare the performances of speed mapping with Optim.jl, with L-BFGS, and with the nonlinear conjugate gradient. So I've also tried with NLOpt.jl and Jump.jl, but yeah, for that exact problem, it didn't work so well. So for the benchmark, I'm going to generate 1,000 random starting points distributed between -5 and +5. And the stopping criterion is going to be the gradient norm being lower than 10 to the -8. And we're going to take 3 runs each time and take the best of them. So since these benchmarks take over 15 minutes, I've already computed them. So let's just comment on the results. So here are the time distributions. So left is better. So for the unconstrained case, speed mapping took on average 8 milliseconds, and the second best was Optim's L-BFGS at 15 milliseconds on average. Okay, so for the constraint optimization, the x starting point will be sampled between -5 and 0 to get feasible initial values. And Optim is going to use fmin box. So speed mapping took on average 15 milliseconds. And the second best was the conjugate gradient at 120 milliseconds. So yeah, 7 times more. Okay, so that's it. I invite you to look at the paper and see much more applications of the method. I hope you found that interesting, and I'll be very happy to answer questions about the presentation or about implementation details if you want to try it out for yourself. Thanks.